All right, we're going to go from the big picture to the very small picture now. And I'm going to describe some work I've done with a graduate student of mine, Xiaoyu Guan, and with a former student, Brian Johnson, at the University of Illinois, where you can see our corn growing near the observatory there. I agonized a bit over the title. Before finally settling on new shearing box results. And a lot of what I'm going to be talking about is a bit of a review of things that have been done before. But the talk divides into two parts. The first part is about numerical methods for large shearing boxes. And then I'm going to talk about applications of this scheme to small shearing boxes for reasons that will become apparent at the end of the first part. All right, so why would we want to look at large shearing boxes to begin with? So by large boxes, I mean boxes whose radial dimension is large compared to the scale height, but small compared to the radius. We might want to do this to probe what we call mesoscale disk structure. And I've just listed some questions one might probe with these large boxes as an invitation to those who are gearing up to do large box simulations. First of all, we'd like to know if the turbulent disk is stable. So by that I mean, is it in some sense viscously stable? Do Fourier components in the surface density, whose wavelength is large compared to the scale height, grow with time? Do Fourier components in the magnetic field, whose wavelength is large compared to the scale height, grow with time? If there is a dynamo to be found in these shearing box simulations, it will probably be in the form of growing low-order Fourier components in the magnetic field. Second, how does MHD turbulence interact with self-gravity? If we're going to really study this at high resolution, we need to be able to simulate boxes whose wavelength is large compared to the scale height, or at least larger than perhaps 2 pi times the scale height, which is the characteristic scale of the gravitational instability. We'd like to know how the cold disk interacts with an overlying corona, because if the corona length scales, if they are much smaller than the radius of the disk, are likely much larger than the scale height. And finally, what are the turbulent transport coefficients? So for example, Steve mentioned the diffusion of a passive scalar, but also one would be interested in looking at how an imposed vertical field is transported by the underlying turbulence. Okay, so these are interesting, motivating questions. What are the numerical challenges for these large boxes? First of all, once the radial scale of the box becomes large compared to a scale height, the time step condition becomes quite restrictive because the shear flow becomes supersonic. So the time step will drop in proportion as the scale of the box expands. Second of all, and this is the real problem that I'll discuss in a few minutes, there's a non-uniform truncation error in these shearing boxes. So near the midline of the box at x is equal to 0, and I'm going to use the standard x, y, and z coordinates, not y, x, and z. Near the midline at x is equal to 0 for these boxes, the truncation error is very small in codes like Zeus and Athena. And as one moves away from that midline, and the shear velocity climbs, the truncation error grows sharply. So this can produce features in the evolution of the magnetic field and the surface density. In addition, if we're going to probe questions like this, turbulent transport coefficients and the stability of the disk, long runs are required because the growth rates, if any, are likely to be of order the viscous time scale on the relevant wavelength. Okay, so our solution to these numerical challenges, and it's not the only possible solution, is to use what we call orbital advection. So we split the advection operator into two parts, an orbital piece and a perturbed velocity piece. And here in the shearing box, the orbital piece is just the usual shear flow. The orbital advection piece can be handled by interpolation, and there's no Courant limit on that. So one can study arbitrarily large boxes without the time step going to 0, and preserve more of the radial translation symmetry, which is inherent in the shearing box. So this is a little illustration of the effective shear on a Cartesian grid. And you can see if this is a set of zones in one of these models, and this is the same set of zones a time step later, that the zones can move by more than one zone width. And that's what we can handle via interpolation. Okay, so our code is based on the Zeus algorithm. And this is very similar to the algorithm that's called Fargo, introduced by Masset in 2000. But it does include the magnetic field. And it preserves the divergence of B is equal to 0. This method is going to produce negligible improvement in the small boxes because it's only going to lower the time step by a small fraction. And there's additional expense associated with it. Okay, so that's the orbital advection scheme, and we've tested it extensively. And this just shows the result of one of our linear theory tests. This is a convergence plot, L1 norm versus of the error versus numerical resolution. And this illustrates the 2 points I just raised. First, that it does improve the accuracy of the evolution. This shows orbital advection on in the solid line and off in the dashed line for a pair of models which have a radial size comparable to the scale height. And if we increase the size of this shearing box to 10 scale heights, you can see that the orbital advection scheme is much more accurate than the comparable. It's the L1 norm of an error of one of the variables. I believe this is, I frankly can't remember. It's like delta Vy. It doesn't matter. They all look this way. Yeah. So if you compare this line and this line, this shows the difference between orbital advection on and off for one of our large shearing boxes, and the accuracy is improved. Okay, so do we see mesoscale structure in these models? This shows the evolution of the largest scale Fourier component with wavelength equal to the size of the box, Lx, in an 8 by pi by 1 box with a mean azimuthal field and initial beta of 400. And this is quite exciting. The Fourier component gradually grows over the course of many omega minus 1. By the way, these are simulations without explicit diffusion coefficients. So you can think of this as a model with effective Prandtl number of order unity. Okay, so this grows. So does that mean there's mesoscale structure? And the answer is we can't conclude that yet. If you look at the mean surface density versus radial position in this model and in other models, it turns out that they all have a dip right at the middle. Okay, and this shows results from the Athena code, and I show this not because we can't do these simulations ourselves, but to show you that all these codes have this feature in them. The truncation error varies over the with radial position, and the net effect is to move matter out of the middle of the box. And the reason for that appears to be that the magnetic field is enhanced in the middle of the box, perhaps due to the lower numerical magnetic diffusion near the midline. So you can see this is producing a nice K is equal to 1 Fourier component in the surface density.
So just to be clear, when you double or halve the resolution, these effects, how do they scale? Do they scale quadratically?
Well, that's something that we don't fully understand yet. Some of our models suggest that the growth of this feature is more or less independent of the resolution. And if that's true, that would just mean that there is in fact an instability in the disk and that the phase is being pinned by this feature in the truncation error. But I'm not confident of that yet.
And so this kind of, that it's of order 10%? Is there a way to understand how
No, this grows, it grows over time, and we don't know where it saturates yet. Yeah, Martin.
The bottom plot is just a concept in the following sense. When we measure vector particle simulations, usually take the volume average. Right? On the other hand, if you get out how much energy you are input in the simulation, you get out the evaluation of the stress at the boundary of the box. And those two things would move, I guess, rather different for the second plot. The step to look at the function of the right direction, something more or less, with well-defined average. Then the volume average and the stress relative of the shifting of the box or the side of the box is not very true.
Yeah, I think that's correct, yeah. So they differ because matter is being rearranged inside the box.
The point of the shifting box is that, if you look at different radial directions, all of these pieces should be more or less the same, right, in the radial coordinate. Slices in the shifting box, they should be more or less the same.
Yeah, if everything's in a steady state, yeah. Yeah. So if I take your point to be that this evaluated along the edge of the box is not the same as the volume average, I agree. Yeah. What's that? This is without orbital advection. Yeah. Yeah. With orbital advection on, the features in the truncation error become periodic in radius. So it depends. Basically, it's at intervals of some multiple of the scale height. Yeah. Okay, so possible solutions to this problem are to throw out the code and use a spectral code. It will be hard to study evolution of the surface density with a spectral code. We could use a shearing coordinate code or try and minimize the features in the finite difference code. And our strategy has been to shift and clean. So what we do is regularly move the model by an integral number of zones, so that the variation in the truncation error is smeared out over the box. And as long as we can do this on a time scale which is short compared to the time scale on which any potential instabilities grow, then we should be okay. So what we do is do this at times when the shearing box boundary conditions line up and it's perfectly periodic. And then we clean away the divergence of B before shifting. Now, why is there a divergence of B, you might ask, if we're using constrained transport? And the answer is that all the shearing box codes have a feature at the boundary, which is related to the shearing box condition, shearing box boundary conditions. And essentially, the magnetic fields on each side of the box become gradually inconsistent with each other over long enough runs. So we remove that inconsistency, which is quite small over timescales of 1 over omega, but can grow over long periods each time we shift the box. And then we eliminate the mean field before shifting. And once we do this, the Fourier components and the surface density still grow. But as I mentioned to Elliot, the results are resolution dependent. I don't really have any results I'm comfortable reporting yet. Okay. So, so now I'm going to talk about applications of our shearing box code to isothermal unstratified shearing boxes. And first of all, I just wanted to show that we can do what everybody else with a shearing box code does now, which is check Fermang and Papalouizou's results, which is a result I first heard about from Takeyoshi and from Jim and resisted strongly. But now I can do it myself, and there it is. So this shows the evolution of the mean magnetic energy with time at various resolutions. It's the same experiment that Fermang and Papalouizou did. This is 3264, and then you gradually see the alpha go away at high resolution. Okay, so I'm going to emphasize a single aspect of the analysis of these shearing boxes, which is an examination of the magnetic field correlation function, because this tells us something about what a characteristic structure in the magnetic field looks like. And this shows correlation function in one of these zero mean field boxes. This is a 1 by pi by 1 box. And the large blue box shows the simulation box itself, and then this little dot here shows the size of a zone. Okay, so you can see that this characteristic structure is tilted along the shear and extends to scales which are of order the size of the box, which means that the boundaries are influencing the outcome of the simulations. Okay, and we can zoom in here and look at the center of this correlation function, and you can see that the width of the correlation function is comparable to the zone size, which is a way of restating the power spectrum analysis that was done by Fermang and Papalouizou in their paper. There's some characteristic correlation length here, which is comparable to the zone scale. It's the one. These are linearly spaced contours, so the 1 over e distance is about here. There's 20 contours between the maximum and 0. Okay, so we can take cuts through this correlation function along the minor axis of that feature, the major axis, and along the z-axis. And that's what's shown here, which should give you a clearer picture of the e-folding distance. And then we calculate a correlation length by integrating along these features. And you can see that the structure of the correlation function along the minor and the z-axes is essentially identical. So these characteristic features in the magnetic field are little cylinders. The minor axis has a correlation length of 0.04 scale heights, z-axis 0.03, and the major axis 0.22. And it turns out that these things scale as the resolution. So if I increase the resolution by a factor of 2, the correlation length drops. So it's always about four zones in scale along the minor axis and the z-axis, which tells us that we're not resolving the turbulence.
For how many different resolutions you checked?
We've checked for 3 different resolutions. And it might not be exactly, we can't tell that it's exactly scaling linearly with resolution just based on that. So take it with appropriate skepticism. Okay, and you can see this feature just looking at the simulation. So this shows 3 different resolutions. 64, 128, 256. And you can see that the characteristic features just get smaller and smaller in this color plot of the perturbed azimuthal velocity.
How do you check the power spectrum for the 3 bases, the entire, not just the correlation function, the entire power spectrum? Because I see you can play with this, but the web to plot the power spectrum this soon. I play around with the data in interaction paper, and the full power spectrum actually scales the resolution.
Oh yeah. The amplitude of the power spectrum also drops. Yeah. Yeah. I think that's just the Fourier transform of what I was saying. Okay. Then I just want to spend a couple minutes on mean azimuthal field boxes. I think these models are possibly the most relevant to real disks. Look at the global simulations, local models in which field can escape through the boundaries, or the galaxy, which has a large-scale mean field. And for these models, the evolution of the magnetic field doesn't behave in the same way as the zero mean field boxes. I don't know if it's converged, but the mean magnetic energy at least increases by progressively smaller fractional amounts as one increases the resolution. And so this is perhaps a little more hopeful. Okay, and for these guys, the correlation function looks very similar, except if we zoom in on the central part of the correlation function, the width here is a factor of 2 larger. So now this correlation length along the minor axis and the vertical axis is 8 zones in size at our maximum resolution. So we don't know that it's going to stay that size as we increase the resolution, but we're going to continue to push those models forward and check. Okay, and again, you can kind of see this in the looking at the perturbed azimuthal velocity. The features do not secularly decrease in scale as one increases the resolution. Yes. Yeah, it increases as you increase the field strength. Yeah. So then we looked at what happens when you increase the box size, and people have looked at this over the years. And there is a weak dependence on the box size. The magnetic energy increases slightly as you increase the box size, although it seems to be converged or getting close to convergence for our largest boxes. Okay, and you can again see that in the perturbed azimuthal velocity, big box versus small box. The features, at least qualitatively, look similar. Which brings me to my conclusion. So I talked about this orbital advection scheme for 3D boxes. It improves accuracy and performance in the large boxes. We've got a paper out describing the scheme, but it still presents challenges due to the non-uniformity of the truncation error. We have some results for small zero mean field boxes, and we're consistent with Fermang and Papalouizou. We've looked at these correlation lengths. The tilt of that correlation function is always 15 degrees. It seems to be absolutely independent of everything. And if we accept that as a characteristic angle for the magnetic field, that's consistent with this alpha is 1 over 2 beta result that we've known about for some time. And finally, results for small mean Y field boxes, which may be most relevant to disks. The magnetic energy we find increases slightly with resolution, but not by much. The correlation lengths at least appear to scale with the scale height rather than the resolution at the resolutions that are currently accessible to us. And the magnetic energy depends on the size of the box, but really only for the smallest boxes. Thank you.
You didn't say, give any results, what happens when the box actually does become bigger in the x direction? So what is the difference? What happens to the MRI? Does it become more intense, or?
Right here. I'm sorry I didn't have time to go over this, but this shows the magnetic energy, which you can use as a proxy for alpha as a function of box size. So this is Lx, Ly, Lz, and we keep Lz as equal to 1, and we increase the box size, and you can see the saturation magnetic energy increasing slightly with box size. Yes?
Question relating to your third part of your talk. Behavior with non-zero mean azimuthal field. The linear analysis for that case shows that, of course, the true modes, right, the swing amplified surfaces, which grow exponentially for a while till the radial wave number gets large enough until kx over ky or something. And the length of that growth phase is proportional, if I recall correctly, to the magnitude of kz, which of course is limited by your resolution. And I thought on that basis I understood why well, leave that comment on the side. But the question is, have you explored, you find that the correlation length in the vertical and horizontal directions are about the same in your simulations. I take it the resolutions are about the same too.
Well, that's correct, yeah.
What happens if you make the Z resolution itself finer?
Yeah, that's an interesting question. Yeah. Yeah.
Based on basis of linear analysis, expect that.
Yeah, yeah. I don't know the answer to that question. The questions multiply more quickly than the CPU hours. So, yeah, that's
It's nice, of course, if one can connect what's happening in
to linear theory. Yeah.
Something that one has analytic control over.
Yeah.
I didn't understand when you come on Fargo, you still get the same density profile with the 10% heat in the middle in the large boxes as you usually mention, or does that go away as Fargo is down?
The dip in the middle. When we see growth in these models, I said sigma k still grows. The phase becomes random once we implement this shifting and cleaning algorithm. But again, it's interesting, it's suggestive. There's a host of numerical issues to worry about there.
Then if you have Fargo on, it means it's not due to truncation error alone.
It's not due to the radial feature in the truncation error. It's not just, as you call it, Fargo. It's the addition of this shifting and cleaning that eliminates the truncation error at the center of the box. because even with just this Fargo, the feature is still there. Yeah, it's still at the middle.